Hello. So in this video, we are going to think about hypothesis or hypothesis testing about the unknown population mean. So we believe that the true population mean equals to a number mu0. But and earlier I explained how you can reject or accept this null hypothesis after looking at the data. So I explained that it is basically a comparison between the p-value, which is the ranking of suspiciousness or ranking of unlikeliness of the data, versus your confidence, like significance level, right? So you first decide how much you are going to reject by setting the significance level, and then calculate the ranking. And if it's too unlikely, then you are going to reject. But actually, there are three different ways to present the result of a hypothesis test. Like, instead of calculating the p-value, like some programs do not give you the p-value, but will only give you t-statistic, right? So you can then still, it's up to you. You can still calculate the p-value, or you can make the decision directly from the t-statistic. Or you can think about other other rules, decision rules based on different but consistent rule, but different expression. So we are going to think about three different ways to present the result of a hypothesis test. As I said, it is more related to programming and presentation and convenience, which is more convenient in your situation and which is more easy to calculate in a certain setup. So they are, in the end, the conclusion must be the same no matter what method you use. But it is, as I said, more like the more depending on the context, and you just choose one of them. The first approach is the p-value approach, which is what I explained earlier. But to summarize it again, you are going to calculate the sample average x bar from the data first, and then you are going to compare the sample average against your hypothesis and standardize the difference. So the second step is the t-statistic, calculating the t-statistic, right? So data minus your hypothesis and standardized by the standard error of your sample average. That is t-statistic. And third step, you calculate the tail probability from the standard normal distribution using the t-statistic, right? So it is about ranking of the unlikeliness, that is the p-value. So after these three steps of calculation, you make your own decision, right? Reject or not based on the p-value versus the significance level. If the p-value is too small, you reject your null hypothesis. If the p-value is too large, is large enough, then you don't need to reject your null hypothesis. So this is up to you, okay? So choice of alpha is yours, okay? Okay, so as I said, the p-value is a measure of the likelihood, and it is calculated based on x bar, the sample average, and the standard deviation from the data S, and the sample size, okay? That means if you have a new data, if you increase the sample size, then you have to recalculate the p-value, okay? That's how it works. However, the p-value does not depend on your significance level. If you choose significance level 1% or 5% or 10%, it does not affect your p-value because, as you see, p-value does not depend on alpha at all. So it is just your choice. Alpha is your choice. So in most cases, if you enter data into a statistical software and run a hypothesis testing there, then they only give you the p-value because, like, comparing it with alpha is yours. It's your job because it's your choice and it's easy enough, okay? So p-value is like the standard method in many presentations and in many softwares. Okay, that is like say it. You can think it as the full calculation method. You calculate as much as you can from the data. Okay, and then what remains is just choose percentage, significance level, how much you are going to reject, and and then from this approach, it is clear that if you increase alpha, then you are going to reject more because basically you are going to understand alpha as the percentage of rejection, right? How many customers you are going to reject, right? So then and also p-value does not depend on alpha. So if if a hypothesis is rejected at 5%, it must be rejected at 10%. Okay? On the other hand, if the hypothesis was not rejected at 5%, then it will not be rejected at any significance level lower than 5%. So it's always like one directional. So as you increase alpha, always rejection increases. It's more likely to reject. Okay. So that's simple summary of recap of the p-value approach. The second method is to drop the third step of calculation. You just calculate the sample average and then the t-statistic only, right? So, and we do not calculate the third step where we use to calculate the p-value. I'm not going to calculate the p-value. Instead, so in the p-value approach, I compare p-value with the significance level, but instead of calculating the p-value, I will calculate something from the significance level to be compared with t-statistic. Okay, so that is the t-statistic approach. So then intuition is to remember t-statistic is the standardized difference between the data and your hypothesis, right? So our idea is then the natural decision rule is if the difference is too large, then we are going to reject our null hypothesis, right? Reject the null hypothesis if the standardized difference is too large, like say larger than a certain level A, right? Certain standard like bar cutoff A, and if the difference is small enough, close to zero, smaller than A, then we do not reject. So if the t-statistic is in between plus minus A, we are not going to reject the null hypothesis. This will be the decision rule. But what we want is we want these decisions to be consistent with the p-value approach. So then, as I said, these alphas, instead of comparing the p-value with alpha, I am going to compare the t-statistic with a value A, right? This value A must depend on alpha, right? So we, like earlier in the p-value approach, we followed 3 steps and then compare with alpha. But now we skip the third step, we finish our calculation at the second step. Then what we have to do is we have to bring alpha back up, right? And to compare with the t-statistic. So this A will be calculated based on the significance level alpha. And remember, alpha is the probability of rejection, how much you are going to reject. And it, like if you think about standard normal distribution, the outcomes that are rejected are alpha percent, but from 2 tails, right? So from like alpha probability from the tails are rejected. So from each tail, you are going to reject alpha over 2 probability. That means you are going to reject top alpha over 2 probability and bottom alpha over 2 probability, like half and half, right? So the rejections come half and half from each tail. So you may remember this notation, Z alpha over 2. Z alpha over 2 is top alpha over 2 probability value from a standard normal distribution, right? So we have to choose decision rule in this way so that the t statistics based on decision rule is consistent with the p-value decision rule. Okay, so this is the basic idea. So earlier in the p-value approach, we set up alpha at 5%, which means we are going to reject 5%. So that means we are going to reject 2.5% from below and 2.5% from the top. So you have to choose A carefully so that the tail probability on each side equals 2.5%. So we did this kind of exercise earlier, and we promised that we are going to denote this value as Z alpha over 2, Z 2.5%. Okay. And then it's pretty easy to see that when the t equals this value, the p-value will be alpha. So when that means the two decision rules are equivalent, right? So when the observation is exactly at the boundary of this cutoff, then that's when exactly p-value is also at the boundary, right? So when the comparison ends up with the equality, right, in both p-value and t-statistics approach. So I guess it's pretty simple to understand. Of course, the derivation is not important, but just I want you to uh, see the relationship, like especially this graph, right? So then also many softwares are built to calculate the t-statistic. Will give you t-statistic if you enter the data, right? So and think about that. T-statistic depends on the data too, like what you need, X bar and standard deviation and the sample size and your hypothesis. So you need your data, but it does not depend on alpha, your like how strict you are, how much you are willing to reject. Does not affect the t statistic. So this is pretty similar to the p-value approach because based on what you need, what to do. And and also another thing here is p-value is a little bit hard to understand what it means. Like say, if I say p-value is 1%, then as you just saw in the previous videos, it takes like 20 minutes to explain what 1% means. It's actually not a probability, it is ranking, right? So p-value is not a probability at all. So p-value is hard to interpret in a sentence. But t-statistic, it has its own interpretation like the standardized difference. The larger the t-statistic, the more different the belief and the data are. So, like if I say t equals -2, the sample mean is 2 standard error below the null hypothesis. So it's interpretable. It's the distance between the hypothesis and the data. So in some sense, like t-statistic is also more useful than the p-value in terms of interpretability. But comparison is a little bit more uh, involved because it's not as simple as alpha, but you have to calculate the z alpha over 2 from standard normal distribution. Still, t does not depend on alpha, and earlier I explained as alpha increases, you are going to reject more. In this case, as alpha increases, that means the tail probability will increase. So the cutoff must be closer to 0. Like higher alpha means you are more willing to reject. So you do not allow much margin for the t-statistic, for the difference between the hypothesis and the data. So A, Z alpha over 2 will get closer to 0, right? Then you are more likely to reject the null hypothesis. Okay, and well, good news is actually Z alpha over 2 is the same numbers as you did in the confidence interval in the previous chapter. Say 10%, 5%, 1%. So now you have to interpret this as I am willing to reject 10% outcome. I'm willing to reject 5%. I'm willing to reject 1%. Then you have to use like 1.64, 1.96, 2.58 in the for the respective percentage. Okay. So and remember it's exactly same numbers in the interval estimation in the for the confidence interval. If you are willing to allow 10% error probability, you have to use 1.64 when you construct confidence interval. And if you are willing to 5% error probability, you have to use this number. If you choose 1%, then 2.58. So identical numbers and obtained from the identical process like standard normal distribution. So you are using the same thing as the confidence interval. Okay. Finally, the third approach is the critical value approach. Here, I do not do any calculation. I just calculate the sample average. I don't even calculate the t-statistic. So I am going to make the decision directly based on the sample average. So rule is clear. I am going to reject my null hypothesis if the sample average is too much different from your hypothesis. Right? This is actually, in some sense, the most natural way to reject. Right? I like least processed decision making rule, and I don't reject the null hypothesis if the sample average is close enough to your hypothesis. Okay? Then again, you have to determine how close is close enough, or how far is too different. How different is too much different? How close is close enough? We are going to think about this kind of thing. So if X, the sample average, is in between your hypothesis minus M, your hypothesis plus M, then we are going to consider it as close enough. Okay? So X bar, the sample average must be like around mu 0 plus minus M, margin M. Okay? And then I'm going to call this two critical values, upper critical value, lower critical value, right? And the interval, the interval between those two critical values is called the acceptance region, where we accept the null hypothesis because the data is close enough to my hypothesis, right? But outside those critical values is called the rejection region. It's a rejection region. We are going to reject because the sample average is different from the hypothesis by more than M. M is our standard. Okay, so this is the idea. My belief was here, but if you set like critical values at 29 and 31, for example, if you set your critical values here and there, then I'm going to reject here and there outside those 2 points. So your belief is here, then you allow a certain margin around your hypothesis. Outside is rejection region, right? Okay, and now I am going to make those critical values M. Basically, I'm going to choose M, how much we have to allow, how much margin we have to allow around our hypothesis. That determines your conclusion, but we have to choose this M so that the result is consistent with two previous decision rules, like p-value and the t-statistic approach, right? To do that, let's start from the t-statistic approach because the t-statistic rule is already consistent with the p-value. And based on the t-statistic approach, we accept our null hypothesis. We do not reject our null hypothesis if the t-statistic is smaller than, like in between plus minus z alpha over 2. Okay? If the absolute value of the t-statistic is smaller than z alpha over 2. right? When your significance level was alpha. And we know that t statistic is calculated this way. So replace t with the formula, and absolute value is replaced by plus minus z alpha over 2. Okay? This is basically the t statistics based decision rule. We are going to rewrite the decision rule like this. Okay? So multiply the standard error on both sides and plus mu zero on both sides on every term. Then you are going to get x bar in the middle and something on the other side. But it's exactly what we wanted. Mu zero is our hypothesis. I believed the unknown parameter, unknown population mean equals mu zero here, and we allow minus something on the left and plus something on the right. So that's the margin we have to allow when we make the rejection, right? So if the sample average lies in between those two margins, we are good. Two critical values, then we don't reject our null hypothesis. That's what we do. So critical values calculated this way. And then as a result, then naturally the rejection rule goes like this. We are going to reject the null hypothesis if the sample average is smaller than lower critical value, or if the sample average is greater than upper critical value, right? So outside. But if the sample average is in between the lower and upper critical values, we do not reject the null hypothesis, okay? So this much is the margin. Right? We allow a margin plus minus z alpha over 2 times standard error s over square root n around your hypothesis. So like that's the difference you can accept. And you may have thought about the formula from the previous chapter. Actually, they are almost the same, right? When you calculate the confidence interval, you calculate the point estimator and allow a margin like this. In this chapter, when you calculate the critical values, you are going to start from the hypothesis as the center and allow the same margin around your hypothesis. So first, the centers are different. The formula, like the basic structures are the same. Like interval in your estimation problem, your basis is from the data. You start from the data because the research question is open. You don't have any prejudice, right? You just look at the data and you start from the sample mean. However, in hypothesis testing, the starting point is your null hypothesis, not the data. So you use your belief as the center, right? And you allow margin. Margin is basically the same. Margin is from the standard normal distribution times standard error, right? That's same for both cases. And interpretation is of course different. Confidence interval should contain the true parameter with 1 minus alpha probability. So you don't know where the true parameter is, but so actually you don't know if this confidence interval actually contains the true parameter or not. Just you believe that you can calculate that your interval contains true parameter with 1 minus alpha probability. But in the hypothesis testing, these critical values will be compared with the sample average. If this interval contains the sample average, then and you can observe that, right? You can observe whether it contains the sample average or not, and if it contains the sample average, then you don't reject null hypothesis. If the critical values, the interval of the critical values do not contain the sample average, then you have to reject the null hypothesis, right? So in estimation, I don't know where the true parameter is, but in hypothesis testing, you know where the sample average is. So you calculate the critical values based on your hypothesis and compare that with the data, right? But confidence interval is based only on the data. Finally, notation is really annoying. Like, what is good is alpha is consistent. We use alpha here and here. They are the same thing. Alpha in the estimation is the error probability, the probability that this interval does not contain the parameter. And here in critical values, alpha is the probability that you reject the null hypothesis, right? However, confidence level is for 1 minus alpha. Confidence level is either 90%, 95%, 99%. But in the hypothesis testing, we call alpha as the significance level. So significance level is either 1%, 5%, 10%. So sometimes, maybe often, I am also confused. I may say the significance level is 95%, which I wanted to say the significance level is 5%. I believe you can understand, right? Even if I say confidence level is 1%, but what I meant was confidence level is 99%. So anyhow, in most cases, it is clear what I'm saying, but just like it's confusing. Okay, so we learned three different approaches: p-value and t-statistic and critical value. The reason why we learn different methods is because it depends on what kind of data you have and what kind of problem you are handling. And as you see, p-value have to do 3-step calculation, and t-statistic 2 steps, and critical value only 1 step, right? So one method could be more convenient in a certain case. For example, p-value and t-statistic do not depend on the significance level. So if you want to change your significance level after calculating those things, then this is more convenient. These are more convenient. But critical value, when you use the critical value approach, you can just obtain the critical values for a given significance level, and then you can easily change the sample average, right? So if you want to apply the same rule to multiple data or multiple groups, then critical value will be more useful, more convenient, right? Because so same decision rule can be applied to different data, but and calculating sample average is pretty simple. But if you apply the same decision rule to multiple data using the p-value approach, that means you have to recalculate 3-step calculation for each data repeatedly, which is not that difficult, but less convenient. Okay, so that's why we learned 3 different ways of implementing the hypothesis testing, or 3 different ways to present your outcome or making the decision. Okay, so but still they are consistent. Don't forget about that. So I emphasize what's consistent across the 3 methods is that the higher the alpha, the more rejections you are going to make, and the higher the standard errors, the more margins you have to allow between between the data and the null hypothesis. Okay, that's all I prepared in this video. In the next video, I'm going to give you more applicable empirical numerical example. Okay, thank you for watching and see you later.